May 1941. 30,000 feet above the California desert, Major Signe Gilkey pushed his YP-38 Lightning into a steep dive. The twin-engine fighter accelerated smoothly at first, the desert floor rushing up through the greenhouse canopy. Then, at 320 miles per hour indicated airspeed, something went terribly wrong. The tail began shaking violently, as if the aircraft were tearing itself apart. Before Gilkey could react, the nose pitched down sharply, steepening the dive until the Lightning was screaming almost vertically toward the earth. He hauled back on the control yoke with both hands. Nothing. The elevator controls were locked solid, frozen by invisible aerodynamic forces that turned the world's fastest fighter into an unguided missile plummeting toward the Mojave. Gilkey had maybe 60 seconds to live. At these speeds, in this angle of dive, the desert would arrive with the finality of a concrete wall. But then, he remembered something from his engineering training, something about elevator trim. With trembling hands, while his vision grayed from the mounting G-forces as the air grew denser at lower altitudes, he cranked the trim wheel. Slowly, agonizingly, the nose began to lift. The dive shallowed. The controls unlocked. Gilkey recovered at just a few thousand feet, his shirt soaked through with sweat, his hands shaking uncontrollably. He just survived what would become known as compressibility lockup, a phenomenon that would kill dozens of P-38 pilots before engineers even understood what was happening. The Lightning, America's most advanced fighter, the first to exceed 400 miles per hour in level flight, had a fatal flaw that made it a widowmaker in high-speed dives, and nobody knew how to fix it. The problem lurked at the bleeding edge of aeronautical science. When the P-38 dove at high speeds, particularly from altitude, it encountered something that aviation pioneers had never experienced before. As the aircraft approached Mach 0.68, roughly 520 miles per hour, true airspeed at altitude, shock waves began forming over the wings. These invisible walls of compressed air did something devastating to the Lightning's aerodynamics. The center of pressure, the point where all the aerodynamic forces effectively act on the wing, suddenly shifted backward toward the tail. This created an overwhelming nose-down pitching moment that the elevator couldn't counter. Simultaneously, the shock waves separated the airflow over the wing, reducing the downwash at the horizontal stabilizer. The elevator, designed to work in smooth airflow, became nearly useless in the turbulent mess created by transonic shock waves. Pilots described it as if the control stick had turned to stone. You could pull with both hands, straining until your arms trembled and the nose wouldn't budge. The Lightning would simply dive steeper and faster, accelerating toward a speed where the airframe itself would disintegrate. The only escape was to ride it out, waiting for the denser air at lower altitudes to slow the aircraft below its critical Mach number, hoping you had enough altitude to make that work. If you entered compressibility lockup below 25,000 feet, the math was simple and brutal. You died. The engineering community in 1941 barely understood compressibility. The phenomenon occurred in a twilight zone between subsonic and supersonic flight, a regime where the old aerodynamic rules broke down, but new ones hadn't been written yet. Kelly Johnson, the brilliant young engineer who had designed the P-38, had actually worried about this during the aircraft's development. He'd consulted with the nation's top aerodynamicists, but in 1938, the knowledge simply didn't exist. Even getting test data proved nearly impossible. Johnson begged the National Advisory Committee for Aeronautics to test P-38 models in their high-speed wind tunnels. NACA refused. Their engineers feared the models would thrash around violently at transonic speeds, potentially destroying their expensive wind tunnels. It took a direct order from General Hap Arnold, head of the entire Army Air Forces, to force NACA to conduct the tests. By then, P-38s were already rolling off production lines. Young pilots were dying in training accidents attributed to pilot error or structural failure, when the real killer was a physics problem nobody could see. The War Production Board, desperate for every fighter it could get, refused to halt production for modifications. The Lightning's compressibility problem would have to be solved while the war raged on. 17 months after Major Gilkey's brush with death, NACA finally tested a scale P-38 model in the Ames Laboratory wind tunnel. The results confirmed Johnson's worst fears while simultaneously pointing toward a solution. The shockwaves were forming on the wing's upper surface, creating that deadly aft shift in the center of pressure. But what if you could change the wing's geometry during a dive? What if you could manipulate the pressure distribution to keep the center of pressure forward? The solution Kelly Johnson's team developed was elegantly simple, almost absurdly so, given the complexity of the problem it solved. Instead of trying to prevent shockwave formation, which was impossible without a complete wing redesign, they would counteract its effects. They would install dive recovery flaps on the underside of the wing, just outboard of the engine nacelles. These weren't flaps in the traditional sense. They didn't slow the aircraft down like dive brakes on a Stuka. They didn't increase lift like landing flaps. Instead, they changed the pressure distribution across the wing in a way that delayed the center of pressure from shifting aft. When deployed, each flap extended downward at a 35-degree angle in a distinctive V-shape, breaking up the airflow over the lower wing surface. The physics was subtle but effective. By disrupting the smooth flow underneath the wing, the dive flaps created a pressure gradient that counteracted the shockwave effects on top. The center of pressure stayed forward enough for the elevator to maintain authority. The pilot could pull out of the dive. It was a Band-Aid solution, not a cure, but it was a Band-Aid that saved lives. In February 1943, Lockheed test pilots proved the concept. The dive flaps were electrically actuated and deployed in just 1.5 seconds, fast enough that a pilot entering compressibility lockup could hit the switch and regain control before running out of altitude. The flaps didn't eliminate the problem entirely, but they gave pilots a fighting chance. From certain death to survivable emergency, all from a few panels of aluminum that folded down into the slipstream. But turning a proven prototype into production reality became a nightmare of delays and bureaucracy. The dive flaps required electrical actuators, new control switches in the cockpit, structural reinforcements to handle the aerodynamic loads. Each modification took time to engineer and more time to integrate into the production line. Lockheed was already building P-38s as fast as humanly possible, with subcontractors across 22 states supplying components. Changing the design meant changing dozens of factories. The final dive flap configuration wasn't approved for production until June 1944, 14 months after the successful flight tests. Only the last 210 P-38J models, designated P-38J-25-LO, rolled off the assembly line with dive flaps installed as factory equipment. By that point, Lockheed had built thousands of Lightnings that would face combat without this life-saving modification. The Army tried to retrofit earlier aircraft with field modification kits. In late 1943, a few hundred kits were assembled for P-38s already deployed to combat theaters. In March 1944, 200 kits destined for the European theater were loaded onto a Douglas C-54 Skymaster transport for the flight to England. The C-54 never made it. An RAF pilot, mistaking the American transport for a German Focke-Wulf Condor in the pre-radar chaos of wartime skies, shot it down. 200 P-38s in Europe would continue fighting without dive recovery flaps because of a tragic case of friendly fire. Meanwhile, in the Pacific, P-38 pilots were learning to work around the compressibility problem through tactics and another innovation that Kelly Johnson's team had quietly introduced. Starting with the P-38 F-15 model in 1942, Lockheed had added a combat maneuver setting to the Lightning's Fowler flaps. When deployed at 8 degrees, these maneuvering flaps did something remarkable. The Fowler flap was aerodynamically superior to the simple flaps used on most fighters. Instead of just tilting downward, Fowler flaps slid backward along tracks, actually increasing the wing's surface area while also adding camber. This provided a double boost to lift with minimal drag penalty. At the 8-degree maneuver setting, the P-38 could suddenly outturn fighters that had previously danced circles around it. This was critical in the Pacific, where Japanese fighters like the legendary Zero had built their reputation on turning performance. The Zero could execute a full turn in roughly half the time of an early P-38, a difference that meant life or death in a twisting dogfight. American pilots were drilled endlessly: never turn with a Zero, use your speed and altitude advantage, make slashing boom and zoom attacks, disengage before getting slow. But with the maneuvering flaps deployed below 250 miles per hour, the P-38 became a different animal. The increased lift from the Fowler flaps tightened the turning radius dramatically. Experienced pilots learned they could actually outturn a Zero under certain conditions, particularly at higher speeds, where the Zero's light wing loading became a disadvantage. The trick was managing your energy state, using the maneuvering flaps at the right moment, and never getting slow enough to lose the P-38's fundamental advantages in speed and power. When the dive recovery flaps finally reached combat units in late 1944, P-38 pilots suddenly had access to tactical options that had been suicidal before. German fighter pilots in Europe had learned that the easiest way to escape a Lightning was to execute a split S and dive away. They knew P-38 pilots were reluctant to follow into steep, high-speed dives. The dive flaps changed that calculus. Now the Lightning could pursue, could use its tremendous power and weight to accelerate in the dive, and could pull out when the German pilot expected to see a smoking hole in the ground. In the Pacific, the combination of dive recovery flaps and maneuvering flaps transformed the P-38 into the most feared American fighter in the theater. Japanese ace Saburo Sakai, who had shot down dozens of Allied aircraft in his A6M0, wrote with grudging respect about the Lightning. He described his astonishment at encountering an American aircraft that could outrun, outclimb, and outdive the Zero, which Japanese pilots had considered the world's finest fighter. The P-38's ability to choose when and where to fight, operating at high speeds and altitudes where the Zero couldn't follow, destroyed the morale of Japanese fighter pilots. But it was the unexpected turning capability that really shocked Japanese pilots. They would lure P-38s into turning fights, confident in the Zero's legendary maneuverability, only to watch in disbelief as the twin-boomed Lightning matched their turns. The maneuvering flaps had given the P-38 a flexibility that contradicted everything Japanese intelligence had reported about American fighters. Combine that with the P-38's concentrated nose-mounted armament, 4 50 caliber machine guns and a 20mm cannon all firing straight ahead, and you had a weapon system that could outturn you and shred you with a single burst. America's top 2 fighter aces, Richard Bong with 40 confirmed kills and Thomas Maguire with 38, both flew P-38s exclusively. They weren't alone. In the Pacific Theater, Lightning pilots shot down more Japanese aircraft than pilots flying any other American fighter type. The P-38's long range made it ideal for the vast distances of the Pacific. Its twin engines provided a safety margin over endless stretches of ocean, and its versatility allowed it to excel as a fighter, fighter-bomber, and reconnaissance platform. The most famous P-38 mission combined all these advantages with pinpoint intelligence and near-perfect execution. On April 18, 1943, American codebreakers deciphered Japanese messages revealing that Admiral Isoroku Yamamoto, architect of the Pearl Harbor attack, would be flying to Bougainville Island for a frontline inspection. 16 P-38 G Lightnings from the 339th Fighter Squadron launched on a 435-mile intercept mission, flying just 10 to 50 feet above the ocean to avoid radar detection. The range was at the absolute limit of what any American fighter could achieve. The P-38s carried massive drop tanks and flew precisely calculated cruise settings to stretch their endurance. They arrived over Bougainville exactly on time, catching Yamamoto's two Mitsubishi G-4M Betty bombers with their Zero escorts just as they descended toward the airfield. In the brief, vicious fight that followed, both Bettys were shot down. Yamamoto died in the jungle below, killed by P-38s that had flown farther than any fighter in history to achieve their mission. Yet, for all its success in the Pacific, the P-38's compressibility problem limited its effectiveness in Europe. High-altitude bomber escort missions over Germany required frequent combat above 25,000 feet, exactly where compressibility became most dangerous. Early P-38 units in the 8th Air Force took heavy losses, and German pilots learned to exploit the Lightning's weaknesses. The dive flaps came too late to change the European narrative. By the time factory-equipped P-38 J-25s reached England in mid-1944, the P-51 Mustang was already proving superior for high-altitude escort work. The irony was bitter. Kelly Johnson and his team had identified the compressibility problem during the design phase in 1938. They had developed a working solution by February 1943. But bureaucratic delays, production challenges, and the relentless pressure to deliver aircraft to combat units meant that only the final half of all P-38s built, roughly 5,000 out of 10,000 aircraft, received the dive recovery flaps that could have saved countless pilots. The friendly fire incident that destroyed 200 dive flap retrofit kits epitomized the frustration. Those kits represented months of engineering work, thousands of hours of manufacturing time, and the potential to save dozens of lives in the European theater. Instead, they burned in the wreckage of a C-54 shot down by an Allied fighter, victims of the chaos and confusion that defined air combat in World War II. Still, the dive flaps represented a genuine breakthrough in high-speed aerodynamics. The P-38 was the first fighter to systematically encounter compressibility effects in combat, and the dive recovery flaps were the first operational solution. The lessons learned influenced every subsequent high-performance aircraft design. When Republic encountered similar compressibility problems with the P-47 Thunderbolt, they adapted the P-38's dive flap concept for their own aircraft. More broadly, the P-38's compressibility challenges pushed American aviation into uncharted territory. Wind tunnel testing at transonic speeds advanced dramatically. Engineers developed better theoretical models for shockwave formation. Pilots gained tactical experience operating at the edge of the sound barrier. All of this fed into the post-war development of supersonic aircraft, jets that could actually break through the sound barrier that had nearly destroyed the P-38 program. Kelly Johnson took the lessons from the P-38 into his later work at Lockheed's Skunk Works, where he would design the P-80 Shooting Star, America's first operational jet fighter, and eventually the SR-71 Blackbird, which could cruise at 3 times the speed of sound. The compressibility problem that nearly killed him and his design team in the early 1940s became a stepping stone to aircraft that made Mach 0.68 look slow. For the pilots who flew combat in P-38s, the dive recovery flaps meant the difference between tactical flexibility and dangerous limitations. With the flaps, you could use the P-38's full performance envelope. You could dive on enemy fighters and pull out. You could exploit the Lightning's tremendous power without fear of losing control. You could fight the aircraft the way Kelly Johnson had always intended it to be flown, as an energy fighter that dominated through speed, altitude, and firepower. The P-38 Lightning's combat record speaks to both the aircraft's potential and the cost of its compressibility problems. In the Pacific, where the dive flaps and maneuvering flaps let pilots exploit the Lightning's strengths, it became the most successful American fighter of the war against Japan. In Europe, where compressibility remained a dangerous limitation for much of the P-38's service life, it struggled to compete with later designs that had learned from its pioneering challenges. Today, when we look at restored P-38s at air shows, those distinctive twin booms and central nacelle represent more than just innovative design. They represent the moment when aviation pushed beyond the familiar into the unknown, when pilots and engineers together discovered that there were invisible walls in the sky that could kill you just as surely as enemy fire. And they represent Kelly Johnson's solution, those simple dive recovery flaps that let American pilots break through those walls and come home alive. The cable-actuated, electrically powered dive flaps on the P-38J-25 and later models weren't just a mechanical fix. They were proof that even the most complex aerodynamic problems could be solved with elegant engineering. You didn't need to redesign the entire wing. You didn't need exotic materials or revolutionary concepts. You just needed to understand the physics and apply a solution in the right place at the right time. 1.5 seconds to deployment, 35 degrees of deflection. A V-shaped panel of aluminum that changed the pressure distribution just enough to give pilots back control of their aircraft. It was, in a sense, a dumb solution, a simple mechanical intervention to solve a complex fluid dynamics problem. But simple solutions that work are the mark of genius engineering, and Kelly Johnson was nothing if not a genius. The dive recovery flaps let P-38s dominate in the Pacific, helped push the boundaries of high-speed flight, and saved hundreds of pilot lives. Not bad for what was essentially a band-aid on a wing. If you found this deep dive into aviation history fascinating, make sure to hit that like button and subscribe for more stories about the engineering innovations that changed warfare. The P-38 story shows us that sometimes the most important breakthroughs aren't the flashy new designs, but the unglamorous fixes that make existing systems work the way they were always meant to. Kelly Johnson understood that, and American pilots in the Pacific owed him their lives for it.